Hmm. Hello, hello, good morning. Testing, testing, 1, 2, 3. Hello, hello, good morning. Testing, testing, 1, 2, 3. Alright, seems like we're all good here. Cool. Well, good morning, folks. So it's 9 a.m. live with Duprez, finishing up chapter 12 today. Figured we'd start off with just looking at the weather, just trying to keep our spirits up while we're locked inside. So, here's your forecast for today. It's looking to be quite sunny. It's going to hit a peak of 53 degrees, so definitely go outside. Try and get some fresh air, but remember, social distancing is important. So, hey, a little bit better than yesterday, and every day we're getting a little warmer, a little happier, right? So, how many people do we have right now? Here we got a couple. I'm just going to get started then. Alright, so we were finishing up chapter 12. We were looking at nuclear power plants. That is where we left off. And then afterwards, the notes, we are going to spend a little time looking at one of the things that a lot of the teachers on the AP group I belong to on Facebook that I always talk about, they are thinking experimental design is most likely going to be one of the FRQ topics. And we touched on this a little bit in the beginning of the year, but since the new format is probably going to ask something that doesn't necessarily have one specific answer to make it so that you can't really cheat, they're probably going with something more open-ended. So they're thinking experimental design will be it. So we'll all go into Google Meet later. We'll work on that together, and that's pretty much what we have on the plate for today. So, Module 36, Nuclear Energy Resources. That's where we are. So, this is a funny little video from The Simpsons, and I bring it up, and you can watch this later, because I think when we think about radioactivity, we always think of the cartoon version, right? That it's like this green, fuzzy force around different objects, and that you can easily see if something is radioactive. And for cartoons it works, right? It definitely gets across that energy part of it, but it's not quite reality. So here's a banana. Bananas are, in fact, radioactive because they contain potassium-40, and that is a molecule that does like to break down, and so bananas are slightly radioactive. Now, is it going to kill you? No. You need to eat quite a few, I think 100 bananas before you even start getting any effects. So you are surrounded by things that are radioactive, but they're not necessarily as dangerous as you think. But also you don't see it, right? It's invisible. Another thing that is radioactive is a smoke detector. The way a smoke detector works is that there is a small piece of americium, and that is radioactive, and it decays, and all things that are decaying, all these different potassium, americium, they all have a constant rate. A smoke detector works in the fact that it has a sensor that picks up the small amount of energy that is given off by the americium breaking down, and as long as it's getting that steady stream, it doesn't beep. When you have smoke in the mix, it can't get that energy, that little note from americium that it is breaking down, and so it beeps. So yeah, things around us are radioactive, and we don't really see it. So, nuclear reactors use fission to generate electricity. Usually uranium-235 is the fuel source. It is a molecule that is unstable and likes to break down once a neutron is introduced into the mix. So, fission, a nuclear reaction in which a neutron, right, which is a very, very, very small thing, smaller than an atom, is going to strike a relatively large atomic nucleus, which then splits into two or more parts, releasing additional neutrons and energy in the form of heat. So this is how the process works. You get these larger atoms, right? Uranium-235 is a bigger atom than, say, carbon or hydrogen, something like that. Those are much smaller. It's going to get hit. That's going to break down into smaller things, and it's also releasing more neutrons, which keeps it going, as well as energy as well. Then, once you're doing that, once you have these fission reactions going, you'll have a power plant taking that energy, using the heat to boil water, and then the same thing we've been seeing with all the other fuel sources. It's going to create steam, turn that turbine, that fan-shaped kind of dumbbell-looking thing, and then that's going to turn a generator, which makes the electricity. Again, you need to know all of those steps. You need to understand that it's the steam that spins those fan things, which then goes into that generator box. Magnets go around and give us the current that eventually leaves and powers our electronics. So, nuclear fission, here's a picture, just in case that was not clear enough. You can see at the top there's a neutron coming in to that yellow and purple uranium-235 nucleus. And once it hits into it, you'll see that energy and then two fission fragments come off of it. So these are two smaller atoms that would, when combined, were the uranium-235. But that also sends out all of these little ends, these other neutrons that go out and hit other uranium-235s. So this could be a runaway reaction. This does lead to it making more and more and more of these reactions, creating more and more and more energy. But, and there's a few videos you can watch that I have posted in the notes, right? There are ways that they control these reactions. So there are the fuel rods, which are the cylindrical tubes that enclose the fuel source, which is, again, that uranium-235. But then there's also the control rods. So these are between all these different fuel rods, and what they do is that they absorb the excess neutrons so that the rate at which the reaction happens is steady and doesn't cause any issues, or at least that's the hope, right? It's controlling the amount of energy so that they can get the right amount of steam, the right amount of heat, so that they're not destroying their internal mechanisms. So if we take a look at what this thing looks like, first thing I want to point out is that this is highly protected. It has a case on the outside, it has a case on the inside. There are many, many safety measures that are implemented to make sure that if something goes wrong, that it is not as bad as you would think. So you can see at the top, you can see the control rods are black, going in between the fuel rods, which are in orange. Those are having that reaction go. And you can see at the bottom there is that gas circulator pushing gas through, collecting it, interacting with a tube of water, which will create steam, and as we mentioned, turn that turbine, spin that within the generator, create electricity. So this is what the setup looks like. And again, it's pretty much the same for every type of these ways that we are generating through the non-renewables, right? That you are going to be creating some sort of reaction that's going to create heat, that creates steam, goes through the turbine, goes through the generator. I know I sound like a broken record, but I really want you to understand that. And again, folks, if you have any questions while I'm going through this, please go ahead and answer in the chat, or sorry, ask in the chat, and I'll be happy to answer you. Just to make sure that you're alive. Everybody, I don't know, throw a smiley face in the chat. Hey, there we go. All right, folks. Good, we're alive. I like it. All right, so nuclear energy has advantages and disadvantages. Well, the advantages are that there's no air pollution because you're not combusting anything, right? There's no need to import oil because you're not using oil, right? You're using this uranium-235. The disadvantages, though, are the possibility of accidents, which we'll get into in just a second. The difficult to dispose of waste. The waste product you get isn't completely safe and not reactive anymore. It still is radioactive, so you need to put that somewhere or deal with it. And then there's a concern about nuclear material being misused. Well, if there are places that want to have this uranium to use as an energy source, there might be some places that say, hey, we really don't trust you with this radioactive material. You could be using it for things that you're not saying you're using it for. So there's a little bit of politics that gets mixed up in that, and there's certainly a concern, since that could lead to some disastrous consequences if the wrong people get their hands on it. So, in terms of nuclear power plants, we do have one that is standing but never really ran. It was in Shoreham, and it looks like that. It's kind of just like an old funky building. You can see all the cool, like, retro controls. It was built and it never really got running. They did some tests, but after the events of Chernobyl and 3 Mile Island in Pennsylvania, people were not feeling safe about having nuclear power, especially on Long Island, where if you have something that happens on Long Island, well, you need an evacuation plan. You need to have a very, very dense area leave somehow. And the people in that area just said, we don't condone this. We don't want to have to evacuate and change our lives if something goes wrong here. So it cost taxpayers $6 billion to have this thing go up, and it never really produced anything for us. So that's kind of one of the big things with nuclear power, is that it is pretty good in terms of the amount of energy you get from it, right? I think in the textbook it said something like 1 gram is like the same, or is like some number of million times the energy of 1 gram of coal. It's very, very energy dense. But the problem is that we've had these disasters that weren't managed very good, and so there's some public opinion out there that, oh no, I don't want that by me, and for good reason. But we'll see. There are still nuclear reactors going. I think France is mostly powered by nuclear reactors, and safety measures have definitely increased since the 70s and 80s. But thought I'd just throw out some Long Island history to you. So the waste. Radioactive waste is nuclear fuel that can no longer produce enough heat to be useful, but is still radioactive. So they don't use this stuff all the way until it goes down to nothing. They use it when it's the most useful, and as soon as it starts to diminish in its effects, they get rid of it. There are 2 units there that you don't necessarily need to memorize. Whoa, almost sneezed. Oh, we're good. A becquerel, which is a unit that measures the rate at which it decays, and then a curie, which is the measure of the actual radiation itself. So if you've ever heard of them talking about curies, if they're looking for radiation, that's what they're talking about. Again, not anything you need to necessarily memorize. I mean, associating it with nuclear things is good, but they'll most likely give you that if there was to be a math question on the exam. So this does bring us to half-lives. This is a lot less res than I thought it would be, but we'll move on. Half-lives are the amount of time before a parent isotope decays to half of whatever starting material like it started with. So if you have 100% of, let's say, uranium-235, the half-life, the first half-life of it is some amount of time, and it is going to decay by 50% in that time. This is something that you've read about way early, way early, I think even in the summer reading, so I just wanted to bring it back up. The next half-life is not half of 100. It doesn't go to 0, right? It doesn't go 150 to 0. It goes 100, then it halves to 50, and then 50 halves to 25%. And it keeps halving and halving and halving. So things, if they have a long half-life, especially if the half-life isn't days, hours, years, it's thousands of years, something like that, it can take a long time for things that are radioactive to actually break down. And that's usually the case. So it's not easy to hold on to this material thinking, okay, we'll cycle it within, 10 years and then it'll be totally safe. It's not how it works. Half-lives, since it's half of a half of a half of a half, it just lingers on for a really long time. Now, how much of that is safe depends on what you're using or talking about, but half-lives are super important. You can see here a representation of 100 going to half of that 50, going half to that 25, half of that 12.5, so on and so forth. So, what do we do with all this stuff? Well, we put it places in the ground, and we kind of just leave it there. They've thought about putting this stuff in trenches, deep sea trenches. They've talked about taking it and putting it all over the place, shoot into space, who knows. But the biggest concern is that it is radioactive material, and they don't want it getting into water systems. They don't want it interacting with people. So there was the Nevada test site, Yucca Mountain, which you can see over there, is in Nevada by the California border. And they were storing things there for a good long time, but in the 2010s, it got defunded, and now it's been in this kind of political limbo where scientists come in and say, hey, maybe we should start this again, and some parties want to keep a open place for this, but it's kind of just back and forth between should we or should we not keep all this, not as radioactive, but still radioactive waste underground. So that definitely leads to some social issues. All right. So I thought this was a really, really cool map in the fact that it shows all of the places that are storing radioactive material from these reactors. So you can see there's a whole bunch of different places here, and there are even some in New York that I really wasn't too aware of. So you can see there are quite a few different places that we hold stuff, and they're most likely outside of regular towns. They're probably underground in some remote area. But number 8 right over here in Oconee, yeah, it's a little close to home. But anyway, thought that would be an interesting link. You can check that out later through the PowerPoint. So going back to the notes, radioactive waste, high-level radioactive waste comes from the used fuel rods, right? Anything left over is still technically considered high-level. Low-level is going to be found on everything kind of around that area, right? They can't 100% contain all of the radioactive material, so they do go through and make sure that any clothing that they're wearing or other items are cleaned, but you have to be aware of that because anything leaving could be bringing radioactivity outside of the plant itself. Uranium mine tailings, right? We were talking about mining and the tailings, all that stuff that's left over from the mining might have some residue, so they need to be cognizant of that, right? You have to actually mine uranium-235 out of the ground. That's how they get this stuff, so that's maybe another negative that wasn't brought up before, right? You might not be getting all this oil from the middle of the ocean, but you still do have to mine, and that could lead to some other issues. And disposal, again, has to be handled with super great care, since this is stuff you really don't want around people. Oh, yeah, so the waste is put underground? Yes. Most of the time it is just underground in tunnels, and they put it in these underground buildings. They lock it up, and they're all in these very, very protective barrels, sometimes encased in cement. I mean, they go through some pretty rigorous methods to make sure that the stuff doesn't leak or cause any issues. Oh, it could be. I may have missed that detail. But they definitely don't leave the stuff in any place where if it did burst or open that it would be in an active waterway, right? They're not putting this stuff next to streams. I mean, now they're not. We'll see. Or I guess we won't now that we don't have to do 8 through 9, but there's definitely some sites that had radioactive material going through highly populated areas, and it was not good. Well, anyway, I'll look at that later. So, fusion power, the last thing we have to talk about pretty much, is potentially the future. It's a reaction when lighter nuclei are forced together. My Dragon Ball Z picture at the bottom, fusion, huh? I don't know if you get that joke, but I thought it was funny. Anyway, 2 smaller things are going to bump together to produce a heavier nuclei. It's the opposite of fission, right? So this is what powers stars. They are fusing the lighter elements into heavier ones. And the cool thing about that is that if humans could tap into this, it would pretty much be an unlimited source of power and of energy, but there are many technological advances that need to be made. Since it produces so much heat, they need to keep it in an area where if something goes wrong, it's not going to lead to some disastrous consequences. Like, it's definitely playing with fire, so to speak. So it's really cool, right? They talk about like cold fusion, trying to do it in a way where it doesn't generate all that heat, but that's a ways out. But if humans could figure out how to make fusion work, we would definitely have, like, we talk about the Industrial Revolution, that would be like the fusion revolution for sure. So what does that look like? Well, you take two of these smaller things, you push them together, and you get out a bigger thing. That's essentially it, and that gives off energy. So two smaller atoms coming together produce another one. So at the end here, I have, again, a whole bunch of videos. This one's on 3 Mile Island. This one talks about Chernobyl. This one goes into Fukushima when, 2011, I think, there was the tsunami, the earthquake too, all tied together that hit into their nuclear reactors, and they do a really good job of showing off how exactly that happened for this disaster. So I'd recommend you take a look at that later. And again, the disaster recreated, showing exactly what went wrong with a model. And then here is looking at France and all of their power. So a couple videos, I can't really show them on my stream since I don't know if I would get some kind of strike or something like that for showing other content. But that's pretty much it. So we talked about oil and gasoline and coal. We talked about natural gas and nuclear energy. This right here is just the two charts going over all the advantages, disadvantages, pollution, electricity, and the energy return on investment to give you just like the full scope of everything that you would need to know about these different fuel types. So definitely read over this. Use this as a review before the test. This is a really good chart, and it is in your textbook, I'm pretty sure. Yeah, it's page 424. So super good, just to look over and really take in all the things from this. So before we move on to part 2 of what we wanted to do today, are there any questions about what we were just going over? Oh, and I just looked it up. Yeah, it's stored in Sarah. It's stored in pools of water until it gets put into those barrels and then stored somewhere permanently. So that's the in-between step before they permanently ship it out. No questions at all, folks? Man, you guys are shy in the chat. It's okay. We can talk. Oh, I'm not going to force you to write things here. Anyway, here's what we are going to do at this point. What we're going to do is I have in the Google Classroom, I haven't posted it yet, I'm going to post a Meet link, please, and I'm going to put this out every time we do a Meet link like this. Oh, what are the... I got you. I'll hold that thought. What are the negatives of a radioactive leak? Well, mostly it's just the issues it causes for health. It can lead to a whole bunch of different diseases. They think that it's related to... One second. Specifically... thyroid cancer. It could lead to mutations. It definitely could disrupt pregnant pregnant women and then their child. It definitely could hinder development of children. There's a lot of things that radiation could lead to that's not so good. So it's mostly just like a huge health hazard to have a radioactive leak, if it's like a huge leak, for sure. Well, it's to answer your question, Daniel, it's small molecules, but it does produce a great amount of heat just because you're forcing them together, right? It just, all of these can keep pushing and pushing together and keep giving out energy. I'm not sure exactly the difference between what small atoms coming together would produce more energy. You don't necessarily need to know like that part of it, but it's just the idea that if you have all of these small particles being pushed together and they all are forming energy, that they're all going to continue to make energy, and that's why it gets so hot. I don't know much more specifics than that, I'll be honest. That would be more of like a physics question, but I'm sure we can Google that later. Or right now. Why is fusion so hot? It also has to do with the amount of pressure that's required. So it keeps giving off energy, and that energy is maintained within super, super high pressure. And so if you have all this energy building up in a high pressure, that's going to cause it to get hotter and hotter and hotter as well. The more pressure you have on something, the hotter it gets, even if it's the same amount of energy. Like, for example, if you take a balloon and you squeeze it, same amount of air on the inside, right? Same amount of temperature or same heat on the inside. Yeah, if you squeeze it, it will get hotter slightly. So pressure does increase the temperature of things. So if it needs an extremely high pressure for this to work, that might lead to there just being extremely high temperatures. Which also explains why the sun is so hot too, right? Super high pressure with the sun. All right, folks, so we're going to move on to, like I was saying, Google Classroom. What I'm going to do is this. I'm going to open up a Google Meet link. Please don't put your camera on. Please only use your mic. And if you don't feel comfortable using your mic, you can always just type in the chat. This is my first time running one of these, so just work with me on this. But we're going to be moving over to experimental design, looking at what it means, how it works, that kind of thing. And that's pretty much what the rest of today is going to be, just so that we can cover our bases. We'll come back to experimental design too, since a lot of teachers are thinking it's such an open way to question how you might test something, so there's no way to plagiarize it, so they probably are going to put it on the AP exam. Are they guaranteed to? No, but we want to cover our bases. So I'm going to cut the stream here. Just folks go to I can pull this up at least, I think. Right, just go into the Google Classroom. There will be a link. I'll post it in just a moment. So I'll call it APES Experimental Design. Continue. I have to get out of stream to do it. All right. Well, anyway, that is what I'm going to do now. So I'm going to stop the stream, and I'll see you on there. See you soon.